circuit families. In this section, we'll learn about various different types of logic families. So these are three logic: pseudo-MOS and dynamic logic and past transistor logic. So what makes a circuit fast? We know that current equal to capacitance times dV dt. In digital circuit, our load is always capacitive, so we want to drive the capacitance faster. So the capacitance equation is governed by this equation. The delay would be proportional to C over I delta V. If the C is large, delay is smaller. Delay is large, and current is large, and it becomes faster. And if you have a larger voltage difference, then you get the larger delay. Right. So we want to make the capacitance smaller, or current larger, or voltage variation smaller. And also low capacitance, we want to make it. Right? So these are the issue or thing that you have to consider for fast circuit. The logical effort we have seen is just the concept of representing driving strength that proportional to the C over I, the capacitance it is seen at the input, right? The input capacitance versus the current and driving resistance, right? If the resistance is smaller, you get the larger current, right? As you can see, you know that, for example, of a NOR gate, you know that the for equal rise in fold time, NOR PMOS size must be 4 times larger than MMOS. So we know that the PMOS is the enemy or axis of evil. So we want to reduce the capacitance for the required current level. Now the question is, can we take out the PMOS capacitance from the input? So people kind of tried hard to develop new types of a circuit in a way to avoid that the PMOS device at the input. So we don't want to add more capacitance onto the input from the PMOS. The first trial is the pseudo MMOS. We only use MMOS for the input networks, and the input connected to only MMOS. So in old days, there was no PMOS is provided. Only MMOS is there. In such case, we made that pull-up transistor is always on, like similar to like this. So PMOS gate tied to ground, and so the transistor is always on. But in old days, that kind of pull-up is also made out of the MMOS. But in CMOS, complementary MOS device technology, we were able to use PMOS and use the similar approach from the old days. We make it the PMOS always on by connecting the gate to ground. For this kind of a circuit, for the input is low, the MMOS is off, and pull-up is possible through the PMOS. But when it is pulled down, then the input goes high, and this pull-down transistor is on. At the same time, the PMOS is always on. So we have to overcome. I mean, the MMOS device strength need to be greater than PMOS, so that it can overcome the effect of the pull-up strength provided by the PMOS. So we have to size a lot greater than the PMOS shown in here. The right figure shows that the depend for various P value, and then the voltage transfer function shown here, V out versus V in. So if you have a too large PMOS device, like a P equal to 24, this is kind of too large, because for the pull-up it's fine because it reached to 1.8, but for pull down it doesn't go all the way down to 0, right? It only go down up to like a 0.3, something like that. This is very poor logic, and also very large short circuit current or crowbar current. Because both PMOS and NMOS are on. So if you reduce the PMOS size up down to 4, then you may go out for the pull down. It becomes like close to 0 now. So as a rule of thumb, we typically design PMOS for this kind of a pseudo NMOS logic type. We design the PMOS size to have 1/4 of the effective strength of the pull down network. So for mu equal to 2, if you have a 16/2 for the NMOS, like a 4, then you want, in typical CMOS design, we want it to be like a 8, but we kind of since the pull-up is always on, we want to make it 1/4 of the device size, that is 2, right? So P need to be designed that to be 4. That corresponds to 1/4 of the effective strength of the pull-down network, right? So here 1/4, like a P equal to 4, you get the pretty, just a little nicer transfer function. But again, the problem is when you pull down the output, there's always non-zero current, right? I is not 0 for V out equal to 0, right? This is a very critical problem. So the pseudo NMOS gate has the pull down network, NMOS, this is the NMOS network. Pull up, we have only single device size. For example, inverter like this, let's size that equivalent to the unit inverter of the CMOS implementation 1 to 2. So in order for the, let's say that we starts with the like a 1 and 1/4 would be 0.5, right? That should be for typical inverter PMOS size 2. We want that to be 1/4 of the original, that would be 0.5, right? So in this case, what would be the effective pull down driving strength? Note that when you pull down, PMOS is always on, right? So effectively it eliminates the pull down strength. So pull down strength would be here the 1 minus how much? 0.5. It has have 1/2 and 2, right? If the PMOS size is 0.2, 0.5, its effective strength would be divided by the mobility ratio. So actual pull down strength would be For the PMOS, pull up strength would be 1/4. So overall pull down strength would be 3/4, right? So if we make it pull down strength equal to inverter, we have to size that the MMOS 4/3, right? 4/3. We multiply the everything 4/3. So MMOS becomes 4/3 and PMOS becomes what? For the make it 2/3, right? We multiply by 0.5 here. So finally, for the pseudo NMOS gate inverter, we can size the for NMOS for 4/3 and for PMOS for 2/3. With that size in mind, we can calculate the logical effort for pull up and pull down and average. Right? In this example, for the pull down, logical effort would be input capacitance is 4/3 divided by what? The equivalent input inverter's input capacitance is 3, right? For the pull up, input capacitance is 4/3 still again, and equivalent pull up strength would be what? That one is 2/3 is the pull up device size, so equivalent. So pull up is, let's say, 2/3. So input MMOS would be 1/3. So total equal capacitance equal 1. So logical effort of the pull up is GU is equal to 4/3, right? And pull down is 4/9, right? By having this, pull up is a little larger than 1, but the pull down is less than 0.5, a lot faster, right? So this is the what we derived how we size those to make it the equivalent inverter size, right? So this is how we get 4/3 for the pull up and pull down 4/9. The average logical effort would be 8/9. The overall this is smaller than 1, right? Now the for parasitic delay for pull up is input total capacitance pull up and pull down. The parasitic capacitance at the output is 6/3. Now divided by equivalent pull up device size is 1, right? Device total input capacitance is 1, right? And for the pull down, the parasitic output parasitic capacitance is 6/3 divided by this we got from 6/3 divided by equivalent input total capacitance is 3, right? For the pull down, so we get the 6/9. So average parasitic delay is 12/9. We can find the similarly for the MMOS and NOR gate. In this example, you will do some exercise. So make sure that for pull up and pull down network, you have to find the equivalent strength inverter, right? So what would be this and what would be that PMOS size, and based on that you find that what would be divided, right, for the targeted for the right. So the dividing factor should be derived from the finding equivalent inverter for each pull up and pull down. So the NMOS design, this is the example of a large fan-in pseudo NMOS. Here, this is like an OR gate, multiple fan-in OR gate. So you have a PMOS to ground gate, and we have a many parallel input right? So this kind of a high fanning and pseudo NMOS or NOR gate. So let's find the optimum path delay, assuming output load capacitance is H and input capacitance is equal to 1. So now we have this is what we have. So inverter logical effort is 1 and the pseudo NMOS logical effort. This is average logical effort. So that gives us G average 8/9. So this is like that. The path effort GBH. G is 8/9, H B equal 1, H is output load capacitance over input capacitance like this, and parasitic delay for the inverter is 1, and for the pseudo NMOS this is the average K input. We have a K input, average parasitic delay would be like this, overall equation like this, and number of stage 2. Finally, the minimum optimum delay would be n stage times nth root of f plus p. Then finally what you get is this kind of an equation. Now calculate the power consumption out of the NMOS, pseudo NMOS logic. So when the pseudo NMOS, whenever you drive the zero output, you draw the static power because there is non-zero current there. So static power can be calculated by the current times the supply voltage, right? You have a current coming out from the supply and VDD, that's power consumption. So if you have a very small, each gate pseudo NMOS will have a small current, but if you have a millions of logic using this kind of pseudo NMOS logic there, then you get a very huge power consumption, like a 1 million gate would be 1 million times of the power consumption. So nowadays people doesn't use this kind of a pseudo NMOS because of the power issue. So only exceptional case we are using is the kind of many fan-in multiple input NOR gate. In this case, if you're to make it like a standard CMOS, you had to stack many of them, right? So we use that PMOS, single PMOS pull up and then put them as many as input here. To reduce the power consumption, we make it pull up as a disable, and we can make it disable by additional control signal so that we can turn off the static power consumption, right? When that is not used. This is the only example that I can think of that people use for this is a special case.